So thank you for having me. Thanks for sticking to the end of the conference. I think this subject is maybe slightly less center for many of you data scientists, but maybe still relevant. And I want to speak about a little bit about how I see natural language in this day and age. So my starting point is, I don't mean to tell you that AI is a big thing and everybody's speaking about it today. You know that. I just want to draw your attention to a resource that some of you may not be familiar with. It's called the AI Index. It's something that I started at Stanford about 5 years ago, and they put out annual reports on the state of AI, like 200 pages of graphs and charts, and which is a good resource for people in the area who want to get a bird's eye view of what's happening. It's both the quantity of stuff that's happening in academia and industry and technical advances and so on. One of the things you'll see in the most recent report that came out about 2 months ago, I want to say, are charts on natural language, which is the focus of this talk. And among them, you'll see technical advances. On the upper right is the granddaddy of data sets, the SQUAD, the Stanford question answering data set. You'll see two lines, SQUAD 1.0 and then SQUAD 2.0, and you'll see in both cases steady improvement with the advent of transformers. We'll speak about that in a moment. Arguably meeting and even surpassing human-level performance, either the horizontal lines, as measured by human who answered the same data sets. Similar story with glue, which became then superglue, an amalgamation of multiple natural language tasks. And you'll see here too, steady improvement with the systems arguably doing better than humans. And here I expect there's a divergence in the audience. Some of you know large language models really well, and some of you maybe only peripherally. And so bear with me a little bit. Recently, some people, notably Percy Liang and a very large group at Stanford, he convened to discuss the implication of the large language models. This suggested we should rename them foundation models for two reasons. First of all, because they really are foundations for many things you can do with them. And secondly, they pointed out that they're not only about text, they're also about multimodal models, including images and other things. I think language models still is a term that has stuck, and we certainly will only be speaking about language models. So here are some examples of those. Perhaps best known are BERT from Google and GPT-2 and then 3 out of OpenAI. The bottom ones are the only two super large models, meaning 100 billion parameters and more, that are actually available to developers. On the right, of course, is our company, AI21 Labs, with our own first model we released openly called Jurassic 1. So for people who haven't seen large language models or don't have intimate experience with them, I'll just mention that they're very large. For example, Jurassic 1 is 178 billion parameters, neural net, trained in a self-supervised, is the only way to train such a huge thing on terabytes of language. Language tokens of language are either a word or a subword, or in the case of Jurassic 1, a multi-word expression, but small chunks of language. And they, what's important to notice, when I first encountered language models, I found it misleading because the names seem to suggest that they learned the rules of language, like grammar and spelling and things like that. But of course, they learn much more than that. They learn about the world as described by the text that they were trained on, and that's the main thing they're good at. And so really what they do, if you want to think about it technically, they give you a probability distribution of a language. Give any sequence of words, they'll tell you what the probability of that sequence. Hide certain parts of it, either the tail end or part in the middle. It'll give you the posterior probability of what could appear here given the rest of the context. And it So fundamentally, they're good at pattern recognition. Now, this might seem like a very underwhelming value they provide, but I think one thing that we've realized is how much power there is in such pattern recognition. And so, for example, and this is an example from our own Jurassic 1. People speak about zero-shot and one-shot and few-shot learning. So here you're given an example of the non-bold stuff you type in. This is actual recording from the system. So you want an idea for a blog post on electric cars. So you happen to have ideas from a blog post on AI and tourism, and you feed it in. And then you say, just prompt it, ideas for a blog post about electric cars. And you get surprisingly cogent suggestions of what the ideas might be, just from the language model. These are the very surprising things that come here. Here's another example. You want to summarize restaurant reviews. Similarly, you give it one restaurant review, Luigi's, an Italian restaurant, with your extraction of the summary key points of the review. And then you give it another restaurant, a Mexican restaurant, La Taqueria, and it suggests some summary points of this review. Again, surprisingly right. But this gives you a sense of the capabilities, this variety of application of language models is, of course, just limited by our imagination. Here are some applications that we at AI21 Labs surfaced. You may be familiar with WordTune. In general, we think of the opportunity as rethinking how we produce information and how we consume information. And in particular, how we write and how we read. Because we say, only somewhat tongue-in-cheek, that the way we write is the way a product manager at Microsoft decided in 1980. And the way we read is the way Gutenberg decided in 1440 with the invention of the printing press. Somebody put it on a piece of paper or screen, and we look at it. And both experiences, we believe, can be radically rethought if you take AI and put it at the core of the experience. So WordTune, which was released about 1.5 years ago, was our first offering, in this case, of writing assistant. And since it's become very popular, the numbers are shooting through the roof. I suspect some of you already had just show of hands, how many of you have had a chance to play with WordTune? Just raise your hand. Well, a good percentage. And the rest of you, come on. It's doing very well. More recently, and some of you may have seen this also, we released WordTune Read. So WordTune Write, sometimes people think of it as a replacement for spell checkers and grammar correcting kind of tools. It's much more than that. It helps you really think about what you're trying to say, because you have this high-dimensional space of ideas, and you output such a poor sequence of words, and the chance that those sequence of words will match with your rich thoughts is essentially zero. And so the system helps you explore other ways that may come closer to what you actually had in mind. It's a fairly magical experience. You should try it out if you haven't. WordTune Read helps you read. Again, these are both the first steps in a long product journey, but already quite transformative. And WordTune Read basically takes this very long 100-page document, and which would take you several hours to read. And it'll give you not a TLDR of the whole thing, which is less useful, but alongside the document, whether it's a PDF or a web document, summary snippets, which are smart. They're abstractive, not extractive. So it's not just taking words or pieces of text and putting them to the side, but actually rephrasing the key idea in a way that you can easily read. And so that's out there. And you may have seen this, but I found myself giving a lot of talks. So several of you may have heard me speak not long ago, and it could be really boring. So here's something you haven't heard me speak about. And that's something that we haven't released. I mean, we've released, but we haven't really released. We're just trialing it. And you can play with it. It doesn't even have an official name, but I'll call it WordTune Watch. And let's take a look. I hope the sound works. If it's not too bad, but I don't want to stop in the middle, so I'll tell you what you're about to see. This is an interview that Chris Anderson, the founder of TED, is doing with Elon Musk. And it's about 1.5 hours long. and fascinating, of course, but you may not have an hour and a half. And so you may want to kind of skim it more quickly. But how do you skim video? So what you'll see here is you'll see the YouTube in this case. On the right, you'll see, again, summary snippets of the video. It's not transcription per se. It's, again, taking the transcription and abstracting it so you can actually see the key ideas and read them easily. And then you can go and scroll down and say, oh, I've heard enough of this. So you'll see, for example, Elon speaking about AI and why AI is central for self-driving cars. The key idea is, the way he describes it, that of course the road system were optimized for us, and we have brains and we have eyes. So that means that our self-driving cars need to have not just neural nets, but also, not just brains, but also vision. That's the key idea. And he speaks about fairly in a lengthy way. And you may find that you already got the idea and you say, well, what else is he speaking about? You can scroll down and see something else.
An 8-minute excerpt of that interview. So here from Austin, Texas, Elon Musk.
I want us to switch now to think a bit about artificial intelligence.
Then it starts tailing off,
right.
and
that's good.
And you start
there's a kind of
getting diminishing returns. In retrospect, they seem obvious, but in order to solve full self-driving properly, you have to solve real-world AI. Because you say, like, what are the road networks designed to work with? They're designed to work with a biological neural net, our brains, and with vision.
Okay, got it.
And so, in order to make it work.
So, Elon, a few hours ago, you made an offer to buy Twitter. Why?
How'd you know?
Okay, you get the idea. So there's a ton of stuff you can do with large language models, and a lot to speak about it. So there's good reason to be excited, and we're excited. We wouldn't be here if we weren't. But now I want to keep it in perspective. So let's look again at the SQUAD, the Stanford data question answering data set. So like we said, on the face of it, tremendous progress, and there is tremendous progress. But this is a paper that came out right at the beginning when the neural net started to catch up, and Percy Liang and his student put out this paper and introduced a cautioning note. So the way the SQUAD works, you give it a paragraph like this one and a question, and the task is to say where in the text lies the answer. And the answer in this case, we won't read it, but is indeed John Elway, the quarterback, and great answer. But now what they did was they put a distractor sentence at the end. Quarterback Jeff Dean had jersey number 37 and Champ Bowl 34. I don't know what Champ Bowl is, and it's funny because this has nothing to do with Jeff Dean who runs Google Brain. But it has nothing to do with the question or with the paragraph or the answer. And still the answer of the same system that did well is the wrong answer. And they did other stuff, and they showed that if you introduce grammatical errors, the F scores drop to garbage. So progress, but you want to take it with a grain of salt. Let's look at output of GPT-3. And I want to make clear this is not a knock on GPT-3. The same sort of stuff you'll see in Jurassic 1 and the other models. So which US cities have more than 20 million citizens? It'll give you a good list of cities. The only problem is there is no city in the US that has more than 20 million people. But that's what its training data suggested it should say. How many teeth does a person have? 32, which is impressive. And when I say impressive, I don't mean to be cynical. It is impressive. How many people does a math teacher have? 47. It has no idea what today is. What is the date today? I'll give you some random date suggesting on the distribution in this data on which it was trained. It can do arithmetic, which again is impressive. Give it 2 digits to add up, and it'll add them great. Give it a 4 digit, it'll be as confident and give you total garbage. It doesn't know how to do arithmetic. And so what this means is we have statistics at scale. We don't have intelligence. We don't have understanding. We don't have reasoning. And this is where we want to go. We want to have these intelligent systems. How do we get there? And here, the world diverges. There are the, I don't want to call them extremists, but there are the extremists who will say that you just need more. Bigger networks, maybe more modalities, not just text, also vision and sound and what have you. You don't want just 200 billion parameters, you want 10 trillion. You don't want to train it, as we did, on close to 1,000 GPUs for several months, but you want 10,000 GPUs for 2 years and spend hundreds of millions of dollars, and that's how you'll get intelligence. And there are those that say no. You will improve, but you will plateau. No matter how much more you give the system, it'll never do arithmetic as well as a calculator that HP introduced in 1970. What do I believe? They told me to be on time. I believe that the right-hand side is right, that you want to introduce so-called symbolic reasoning into the neural mix. Neural networks are a necessary component in modern-day AI. There's no question. But it's necessary, in my opinion, not sufficient. You want to augment it with the elements that it's missing. It's not a mistake that the most advanced species on Earth has language and uses the language for reasoning. And it's interesting because if you look back at the AI index, which I mentioned at the beginning, you look at historical data of activity in AI as measured by attendance in conferences or the how many people take courses in AI or how much venture capital money is poured into AI. They're all U-shaped. Back in the 80s, AI was very popular. Maybe not quite as it is today, but it was very popular. And then we reached the so-called AI winter where you weren't allowed to admit you're doing AI. And now, my plumber is doing AI. But it looked very different at the time. AI in the 80s was all about symbolic reasoning. It was how to represent complex semantic objects like time and causal relations between events, and how to say that this person knows and this person doesn't know, and they know that they don't know, and what algorithms should apply to such data structures. There wasn't a lot of data. There wasn't a lot of compute. You didn't need a lot of compute to do that sort of AI. It wasn't terrible, but it certainly overpromised. What's happened now, we've pivoted to the other side. We do statistics. We left money on the table when we stopped this reasoning. It's time to bring them together. That's my belief. And the question is how. It seems very hard. This sort of oil and water, right? The continuous kind of mathematics, stochastic gradient descent, neural nets, don't live nice with API calls and calculators that do addition and so on. So somehow you need to cross this neuro-symbolic divide. Well, it takes a miracle, so here's a miracle. It's something we introduced a couple of months ago called the Modular Reasoning and Knowledge Language System. And it kind of works like this. If you were to ignore everything under the, I don't dare touch this, the upper red rectangle, you get a normal neural operation. You have this neural net, Jurassic one in this case, that was trained, and now you feed it text and out comes text. But what happens here is, before you let the neural net do its standard thing with one forward pass, you say, well, maybe there's an expert that's really good at this. For example, a calculator. Or if you ask, what the weather, and weather.com through an API, and so on. And you feed it that data, you get back the response, and then if you wish to output text, you feed it through the network by concatenating it with the original input, for example, and get a robust answer. And so that's the basic idea. It sounds easy, but it's not. And the trick is this little thing called their input adapter, because you need to identify that there's, for example, a calculator that has something to say. You need to somehow has a classifier that does it robustly, And then, very importantly, you need to understand what input this expert needs, because the calculator knows, the addition sign and the two arguments, the operands. Somehow you need to extract those in a reliable way from the text. Okay, so you do that. That's a separate discussion. We have papers on this if you want to look at some details. But that's the basic idea. So let's look at examples of how this works. As far as having up-to-date information, who is the President of the United States? Ask a T0 or GPT-3 or our own Jurassic 1, they'll tell you Donald Trump. Ask Donald Trump, he'll probably say the same thing. Google search engines know the answer because they have access to current information. Traditional language models don't. Now Jurassic X is our own implementation of a miracle system. Jurassic X will give you the answer. Joe Biden is the 46th and current president. So you got up-to-date information. What about more complicated reasoning? So the company had 655,000 shares, which they divided equally among 94 employees. How many did each employee get? Simple arithmetic question. Give it to T0, it'll tell you 94 employees. Okay? Give it to GPT-3, it'll tell you 7,000 stocks, not even shares. Not sure why it said that, but it did. Not terribly far off, by the way, but wrong. Give it to our own Jurassic 1, I'm afraid it says 1.5. Google, it's not in the business of answering such questions, so we shouldn't penalize them for it, but they don't. I mean, search engine, not Google, the company. And Jurassic X will tell you the right answer and even tell you how it got there. It'll tell you, here's the operation that led to this result. This explainability is one key advantage. You not only get robust answers, you can explain them also. This is simple kind of reasoning. What about more complicated reasoning? So how does reasoning work in the first place? So you got the input text, and then the adapter realized that there's something to be farmed out to the calculator and figured out what it is to farm out. The calculator does its thing, gives the answer, and then you turn it back into text using Jurassic 1 again. So this is simple kind of reasoning that the expert did. But what about more complicated reasoning? Do more people live in Tel Aviv or Berlin? First, let's look at the answers you get. T0 will tell you Berlin, wrong. Right. Got lucky. GPT-3 will give you the wrong answer. Jurassic 1 will give you the less wrong, but still wrong answer. Google, again, is not in the business of answering these things. It'll give you certain hits that may be somewhat relevant or whatever. And Jurassic X will tell you more people live in Berlin than in Tel Aviv, but more interestingly, or as interestingly, it'll tell you why. First, it found out the population of Tel Aviv. It went to the Wikidata expert and extracted that. Similarly, it found the population of Berlin. Then it fed the question, what is bigger? This number or this number, and farmed it to the calculator. And then it got the answer. So this is how things work. I think that this is a very fruitful direction. And if I were to summarize the talk, and I'm almost done, it would be this slide. We're in an era where we want to mix traditional symbolic reasoning with all the goodness, and there's a lot of goodness of of deep learning. And with that, we can really get above the glass ceiling that we'd be hitting with a purely neural approach. That's it. And I was told to not take any questions, so I won't. But I'll be around if people want to chat afterwards, and you're welcome to do it. Okay, so thank you very much.